Good evening, and welcome to the 2015 Sverdrup Visiting Scientist Lecture Series. My name is Ben Stotrup. I'm a faculty member in the Department of Physics, and we are delighted to have you here. The Sverdrup Visiting Scientist Lecture Series is the final of Augsburg's Convocation Series and is sponsored by an endowment of the Sverdrup family and the Minnesota NASA Space Grant Consortium. There are two goals of the Sverdrup Visiting Scientist program. First, to provide an opportunity for Augsburg students and faculty to interact on a personal basis with a scientist of national stature. Second, the program provides an annual forum where Augsburg and the wider scientific community can expand their knowledge on a scientific topic of national significance. Tonight, we are honored to have Dr. Ann Douglas of NASA Goddard Space Flight Center. Dr. Douglas has a CV too long to recount, though I will say that she is currently the project scientist for Aurora. I'm sure we will learn about that tonight. So, without any further ado, please welcome Dr. Ann Douglas.
Well, thank you. So I am project scientist for Aura, and what that means is like I have a bit of a public relations job. If anything goes wrong with the satellite, the engineers say, what does that mean to science? And I'm supposed to answer that question without any, just like, what does that mean for science? And you go, oh, well, do you really want to know? And I am going to talk a little bit about Aura, but I want to talk a little bit more broadly about satellite data that I've been fortunate enough to be working at NASA during an age of an explosion of information. The first satellite program that I was involved with was in 1979, or I was only involved with the data, that's before I got there. But then the Upper Atmosphere Research Satellite that came later and Aura have just given an incredible amount of information about a previously unknown region. So I'm going to talk a little bit more broadly about those, and then wearing my other hat, which is the co-lead for a chemistry climate model, I want to talk about how we are using satellite data to develop, test, and use these very complicated earth science models. So we start, you have to start somewhere, and I never really know where to start when I have a mixed group. So if you think this is way too easy to think about, then you can have a little snooze and pick it up wherever it starts to get interesting to you. But why do you study the atmosphere anyway? Well, you want to predict the weather. That's the first thing I think that you think about, and that has a lot of implications, not just because people want to know the weather, but it matters to society for all kinds of planning and financial things. But for the stratosphere, which is the main area that I want to talk about, it starts out with wanting to understand what some measurements were. And these questions go way back. It's basically curiosity-driven research of measurements that were being made in the first half of the 19th century, or the 20th century, the 1900s. So, some questions. How much ultraviolet radiation gets to the ground? It was measurements of UV radiation that led people to understand that there was something absorbing UV radiation, which they didn't know what was, but they had these ground-based measurements to start with. Why does the temperature decrease with height? And then even more interesting, perhaps, why does it increase with height when you go above a certain altitude? And why does the amount of water vapor drop suddenly when you cross that same altitude of minimum temperature? These are some of the things that people were puzzling over. You have to understand what's the basic state of the atmosphere first before you can start making predictions. Why is there a stratosphere? Natural variations. What happens when the seasons change? Does the southern hemisphere just look just like a mirror image of the northern hemisphere, or are there differences? How can you explain the global distribution of ozone and water vapor? Because ozone, once people discovered what it was, is produced in the tropics mainly, and yet the highest ozone values are found at middle and high latitudes. And why is the stratosphere so dry? The second level of questions is to understand how the atmosphere may be responding to natural changes. What controls the seasonal cycle of ozone? How does the solar cycle affect the ozone? What about interannual variations? If I measure 1 year, is that enough, or do I need to measure many years? And then I put the ENSO question on because you hear a lot about ENSO and you hear a lot about the weather, and I was lucky enough to visit Peru. And when I was in Peru, I saw these beautiful seashells, and it seems that the Peruvian scientists were really concerned about understanding the relationship between this particular beautiful seashell and the rainfall in the mountains during the years when these seashells were seen on the beach. So what they were seeing was evidence of a current change related to El Nino, and relating that to the rainfall and food security for their people. So people have been thinking about these things for a really long time. But a real driver of atmospheric research, at least during the course of my career, has been to understand how the atmosphere will respond to anthropogenic changes. In the 1970s, the first huge program to understand the stratosphere developed. It was funded by the Department of Transportation. Maybe that would surprise you. But at the time, people had supposed that a good thing to do would be to fly supersonic aircraft in the lower stratosphere. And a few scientists said, well, wait a minute, if you do that, you're going to change the ozone layer. And a huge amount of scientific activity followed that question. And we didn't ever build that fleet of airplanes. You had the Concorde that flew from London to New York. But there's two things. Well, it was never a fleet. There was like 3 of them or something. And the only reason it only flew from London to New York was because that's as far as it could go. I didn't know that for a long time. I didn't know couldn't cross the Pacific, but it couldn't. So that became a non-issue. And then we didn't talk about that for a really long time. The question about the chlorofluorocarbons came, well, in the 1970s. I thought I was pressing the other button. In the 1970s, will chlorofluorocarbons cause global-scale ozone destruction? And people talked about that for a really long time before anybody had any convincing evidence one way or the other. We were looking for a gas phase change at about 1 millibar. What we discovered was the ozone hole, completely unexpected. And I'll talk about that a little bit more later. But that was the big question in the 70s. Again, it's a man-made thing. And then in the 90s, again, will a fleet of supersonic aircraft cause lower stratospheric ozone destruction? Because the aircraft people had figured out a way to make a plane that could fly across the Pacific, and they were very excited about this prospect. And a whole big decade was spent trying to figure out the environmental impact before the airplane companies decided they didn't want to do it anyway. And then that program ended again. So I'm anticipating in about 5 or 10 years another push to figure out what supersonic aircraft would do to the stratosphere. But it hasn't happened yet. And the present questions really have to do with the atmospheric changing due to increases in greenhouse gases. And that doesn't just mean the surface temperature, although that is what you hear the most about. Now I did that wrong button. So there are a lot of things to consider if you're going to try to answer these sorts of questions. There have been many, many measurements that have been made because of these questions. And the way that I like to think of this is that when you have developed a basic state, it's really like a very basic physical problem where when you take classical mechanics, you start out with a system and it's static, and then you perturb it, and you have to see what happens when you perturb the system. And you need to understand how the basic state or approximations you may have made in getting to the basic state are affecting the response. And it's also important to consider that economics plays a role in this, because one of the reasons the nations of the world are interested in this and really willing to invest, well, $1 billion for the Upper Atmosphere Research Satellite, $650 million for AURA. The Europeans put almost $1 billion into ENVISAT. You wouldn't be putting all this money into these satellites just for curiosity-driven science. the countries of the world think that there's a reason that they're going to get a benefit from this and an answer to some of their questions. So here's a picture that we've put together so that you understand how the stratosphere works in one pretty picture. So here's the tropics, and this is where you have most of the air entering the stratosphere, where the heating is the most, and you have general tropical upwelling. And these source gases enter here in the tropics, and the general circulation after that is upward, poleward, and down. You have the ozone layer in the stratosphere. You have the UV radiation coming in and preventing all that ozone from reaching the ground. Every now and then you get a natural experiment, like when the Mount Pinatubo goes off, because you put a whole lot of aerosols into the stratosphere, you change the chemistry, you change the heating, you change the circulation. You have a really great natural experiment that you can work with. These other changes, like if we're changing chlorofluorocarbons, or we're changing nitrous oxide, or we're changing methane, we have no control over these, and we don't have a control planet either, unfortunately. So we can't tell what would happen if we weren't making these changes. Polar stratospheric clouds are really involved in the ozone hole and ozone depletion. I'm not going to talk about that, but if anybody wants to ask me about that later, you certainly may. So how do you know that schematic that we put together that I just showed you is correct? Well, there's a lot of measurements that went into it. Temperature, winds, our meteorology, and composition measurements. And we're measuring long-lived gases like nitrous oxide. Long-lived means it's protected in the troposphere from UV radiation by the ozone layer, just like we are. And so those gases aren't destroyed until they have risen high up above the ozone layer and they don't have their protection anymore. So they're very long-lived in the atmosphere. But they are also important because when they are destroyed, they create other gases, radical gases, which do destroy ozone. So you need to know what's happening with your source gases. You have medium-lived gases like nitric acid and hydrochloric acid, and we call them reservoirs. And they really control what's going on with the chemistry, because when gases are tied up in reservoirs, they can't react with ozone. And then we have short-lived gases like nitrogen dioxide and hydroxyl. These are radicals. These react with ozone and just about everything else. Other things to think about: clouds, rainfall, the surface, if you're going to worry about what's going on in the lower atmosphere. So you learn a lot of things. You do a lot of process studies. Then you have to put it together, and you have to try and develop a global model. A comprehensive global model has many, many pieces. We do have the Navier-Stokes equations relating pressure, temperature, density. These are hard equations to solve, but we do have equations, so we all start from the same place. We have physical processes that we need to account for: convection, entrainment, detrainment, precipitation, clouds. You need to put all these sorts of physical processes into the model. For radiation, you have your incoming solar radiation, but you also have outgoing long-wave radiation, and you have to figure out how to do radiative transfer between the regions of the atmosphere. We have chemistry, literally hundreds of photolytic and chemical reactions. Every single one of those reactions represents a couple of lab experiments at least, and so you can get the idea of how much and how many people are involved in this enterprise. So we have to get appropriate inputs. We have now got panels that get together and decide everyone should use the same kinetics. You have to decide how you're going to solve those nonlinear coupled differential equations and how to parameterize your subgrid scale processes. You have to identify and represent important additional physical processes, and if you want to have a climate model, you also have to have an ocean model because of the heat exchange between the atmosphere and the ocean. So the bottom line, for earth science, you've got to get together with a group of smart people. Interdisciplinary science requires many people, different viewpoints, and cooperation. And the other point I would like you to notice as we're talking about these things, in one way we're talking about physical processes in a way that is conceptual, But the other thing that is equally important is how you implement this in a computer code. So you and I could both have the same problem in mind, but we attempt a different way of solving it. One of us might make a mistake, which happens more than we would like to admit, and we would get different answers. And what we're looking at then is not a difference in physics or the way we understand it, but a difference in implementation. So to develop a predictive capability, people often use the analogy to a three-legged stool. We have to have atmospheric observations, we have to have atmospheric simulations, and we have lab work. And those three things each play an important role in being able to develop this predictive capability. You might not even think of it, but the lab work part comes into play also with the atmospheric observations, that whether our measurements are being made from the ground or by balloon-borne instruments or aircraft instruments or satellite, every single one of those is relying on physical chemistry, both for the experiment and then for understanding and interpreting what you're measuring. So I was fortunate enough to be at NASA, as I was saying, for this whole long period. So Nimbus 7, the data was not released until about 1983, so that's one of the first things that I worked on. The Upper Atmosphere Research Satellite was deployed from the Space Shuttle in '91, and I got to work on that for quite a while. And then Aura was launched in 2004. We just celebrated our 10 years of operations last summer, and we think we could go to 2021, because you never know. MVSat was operating perfectly a few years ago, and then one day they lost contact and it was over. Just like that, just like that. So you don't know what's going to happen. But I also got to live through the days of both one-dimensional, two-dimensional, and three-dimensional models, and I'm going to talk a little bit more about that. And then these are some of the questions we've been trying to look at. So this is a picture of Aura. This is really just a brag picture because I'm not going to talk about it that much specifically, but I think it's really pretty. And so we have 4 instruments. This Hurdles had the best vertical resolution of any space instrument ever. I don't know what's... Laser pointers are really great, except when they stop working. And don't point them in your face. The microwave limb sounder. Okay, so the Hurdles measured with like a 0.5 kilometer vertical resolution, very dense profiles, but they also had a launch accident and stopped working after only about 3 years. So it's kind of we get some great data, but it only makes you wish that it had worked better. The ozone monitoring instrument, OMI, was given to us by the Dutch and the Finns, and so we have an international science team, which is a lot of fun. And that one's still working really well. TESS, the tropospheric emission spectrometer, has given some really novel information about tropospheric composition. We don't know how much longer it's going to last, not much. And the microwave limb sounder, MLS, measures with microwaves, and it has been working flawlessly. So you might have noticed this. MLS is microwaves, Hurdles is an IR instrument, TESS is an IR instrument, and then OMI measures in the UV. So you're looking at instruments with a broad spectral range. Now I pointed at the screen. And this is just a picture because I love to show it. This is the picture of launch. I wasn't actually there. We went to try and see it launch several times, and every time it scrubbed. And then they told us there was no way it could launch tonight. We were out at Vandenberg. We all went home, and they launched. I did see it on the big screen at TV, but I love the picture. Now, even though I didn't get to see it in person, I did get to stand next to the rocket. And I have to say that should you ever get a chance to be involved with a project where they're going to put something into space, this is something that you don't say, let me think about it. You just say yes, because it is beyond awesome to work so hard on something and then be present and see it, integrated on the rocket and then launch and then give good data and last in space for 10 whole years already, 10 years and counting. You think of any experiment you've ever done and how it could last without anybody ever touching it again for more than 10 years and still be operating well. It's really pretty awesome. Okay, so in the early 80s, when we were trying to develop this whole model, the photochemical data was still evolving, major processes were unknown, features of the circulation were unknown, and we didn't have a whole lot of data. But we did know something about the loss process that produced and destroyed ozone. So I just want to review really quickly how the stratosphere ozone photochemistry works. You have this basic cycle, the Chapman cycle, that involves just oxygen. So O2 breaks apart with very high energy UV, forming O plus O. O plus O3 will react and give you two O2s. This is your basic production reaction. This is your basic loss. Ozone also absorbs ultraviolet radiation, but it's a little bit lower energy, giving you O plus O2, and O reacts with O2 in the presence of a third body, so you can conserve mass and energy, and produce ozone, and the third body doesn't change. These two reactions are really fast. They just really switch between O and O3, but in so doing, with all this switching, they're absorbing a lot of that ultraviolet radiation. The O2 absorbs ultraviolet radiation high up. So when you look at this, you think it's a really pretty cool system, that the getting all that nasty UV out so that we can have life as we know it on Earth is a two-step process, where first you have to break apart the O2, and then that makes ozone, and then ozone takes care of the rest of it for you. So it's a pretty nice system, and it also explains that question, why does the temperature increase when you get to the stratosphere, all that heat? And if that's all there was to it, it would be pretty easy, but we have these other things. So we have source gases, which I talked about a little bit before, but like nitrous oxide or chlorofluorocarbons or water, and these react either with ultraviolet radiation or excited atomic oxygen, whoops, that shouldn't be there, or with OH, O singlet D, and they produce radicals. So nitrous oxide gives you nitrogen radicals, the chlorine compounds give you chlorine radicals, hydrogen compound, or water gives you hydrogen radicals. And all of them can react with ozone. You also have reservoir gases, and I just wanted to say what these were because I would probably say it and you wouldn't know what I was saying, meaning. But the radicals can either react with each other, like the hydroxyl radical with nitrogen dioxide to make nitric acid, or they can react with a source gas, like chlorine reacts with methane, and then they produce these medium-lived gases, hydrochloric acid, nitric acid, chlorine nitrate. And these gases control partitioning. And then, of course, the question that we've answered many times, but you probably all know the answer to, how does a radical present in parts per billion affect the amount of ozone that is present in parts per million? And the answer to that is through a catalytic loss cycle. So you have a rate-limiting step, which is the reaction of chlorine monoxide with oxygen, and then you have another reaction of Cl with ozone. The net of these two reactions is O plus O3. And you do a lot of analysis and understanding of what's going on in the stratosphere with the rate-limiting step. The way that you know what? I think we need a new battery, or we need an advance. Like, you can advance it or I can advance it, but I need a battery. So I always think of the catalytic cycles as just being boosters to the natural loss. It's the same net reaction as the Chapman loss reaction, but it gets boosted up by the presence of these other radicals. And the rate-limiting step, I explained this to people many years ago. It's like doing the wash. Usually you can run the washer several times, and the dryer takes longer. So if you have like 10 loads of wash, you can't do it any faster than you can get it through the dryer. So that's pretty much how it works. And this is really helpful in understanding how the ozone layer is working, the rate-limiting step. Can we advance? So back in the 80s, we were getting into this kind of thing and to understanding how the base model affected the perturbation. So the kinetic data was so uncertain at that point that you could get just about any answer that you wanted by choosing the kinetic input differently. So we did this Monte Carlo analysis over all the different possible combinations of reaction rates, and then we looked to see what would happen when we did a perturbation. Would the perturbation depend on the base state? And how did that conform with the data that we had available? And basically, what we found was that the perturbation really did depend on the base state, and that many of these combinations of reaction rates were completely unrealistic given the data that we had. So that starts to give you a way of pulling in the number of possibilities in a model that has so many inputs and that can be so uncertain. Next. So we took that exact same sort of thing, that exact same concept, and we looked at what was happening with the annual cycle of ozone and how that compared with the model calculation. So now we're taking some observations, we're taking a model, we're taking a natural process, and we're looking to see how they relate to each other. And what we found was that the observed amplitude, the simulated amplitude is a lot smaller than the observed amplitude. Now, what you can figure out from all of this is that the cycle in temperature is what's driving the cycle in ozone. And if you look at these rate-limiting steps, the reaction of O with O3 is the most temperature-dependent, and the reaction of O with ClO is the least temperature-dependent. So if you're thinking that this one is too important, you're definitely going to have too small an annual cycle because it's going to be doing more of its share of the work. So this took us back to the three-legged stool, and this is why I'm showing you this one, because chlorine had too much influence, and we could show that, but we couldn't show why. And this caused some kinetics people to go back to the lab and to make some measurements, and what they learned was that when chlorine monoxide reacts with OH, 7% of the time it produces this reservoir gas, HCl, that doesn't react with ozone. So what we had found was a way to decrease the influence of chlorine. So this is a really good example of how the system works together. We're using a natural cycle, we're using a model, we're using observations, and you end up sending people back to the lab. Next slide. Okay, so what about that D in the model, 1D, 2D, 3D? So in the 80s, we had no computer power to speak of. We had incomplete knowledge of the processes, no global data. And the best models were 1D, single profile, or 2D, latitude, altitude. And I want to point out that the Montreal Protocol, which limited the production of CFCs, first limited and later stopped, the theory behind that was 1D and 2D models. That's all we had. We didn't have any really good models then. So that's actually pretty impressive to get that protocol with such limited capability of simulating the atmosphere. And also, like this incomplete knowledge of processes. People often point out none of the models in use in 1985 predicted the ozone hole. Well, you know, like if you actually had a model in 1985, of course it didn't produce the ozone hole because there was all kinds of unknown chemistry and processes that you had to put in the model. Models are not perfect, and if you're missing a process, you're missing the whole thing. You're not going to get it. That's pretty much it. Next slide. So this is a picture that you would see of how ozone is supposed to interact, and this was certainly around in the 70s. And as soon as I got into the field, you needed dynamics and transport because ozone is long-lived in the large stratosphere and you need to know how it's moved around. You have photochemistry because that's really controlling the level. And you have radiation because the ozone is affecting the how much UV is absorbed and is available and reaches the surface, but also because ozone is a greenhouse gas and it absorbs in the infrared. And a fully coupled model is going to let you have these feedbacks between all three things. And for many, many years, what we called this was the Holy Grail because we couldn't do it. Next slide. So when people had general circulation models with chemistry in around 1990, yes, you had better representative of polar vortices, and you had actual advection rather than making up diffusion, but you had a big problem because you had temperature biases that were so severe that if you actually tried to do chemistry in those models, it didn't even look like the planet Earth. So we had some problems. So we came up with a solution, or you could call it a Band-Aid, which was a 3D model that just calculated chemistry and transport and didn't have any feedbacks. But we would use real meteorological data in that model, and then we would be able to see if we were able to predict realistic evolution for some of our constituents. Next slide. Okay, so this is like a little aside. Major improvements in your modeling capabilities can come from unexpected places. So you can just keep that in your mind. Next one. So when they started doing all these aircraft measurements, this is 1987, this is to try to figure out what's causing the ozone hole. What they found was that long-lived gases like to, if you plot them one against each other, they like to make straight lines. And we thought that was pretty interesting. And it's also interesting that there's absolutely no model of that era that would do that. Okay, next slide. Later on, we got aircraft or satellite data. This is from the Upper Atmosphere Research Satellite, one of the instruments. And this is methane and hydrogen fluoride, which is a product of decomposition of chlorofluorocarbons. And what we found was that these tendency of things to line up was present throughout the atmosphere for these long-lived gases, that they would line up on these constant contours. And this was kind of surprising, and it placed physical constraints on the numerical transport and prompted all kinds of improvements in the chemistry transport models that were using simple centered differences or fourth-order differences or spherical transport. And everybody started using instead what are called upwind flux-limited shock capturing schemes. In other words, they transport things much more realistically. We learned about them from people doing plasma physics. They don't undershoot and overshoot. They don't create new maxes and mins, and they have all kinds of wonderful characteristics if you're trying to do numerical transport and then do chemistry. So we put those schemes in, and then, next slide, suddenly we were able to reproduce things like this is a comparison of a simulation with data from total column ozone from the TOMS instrument, which was on Nimbus 7. And this is a seasonal integration. And there we are, really reproducing what's happening with the data. And we were really shocked when we could do that. Prior to this, changing this numerical transport scheme, we were only ever producing zonal mean agreement. We couldn't produce any longitudinal variability. So the main point here is that we needed to fix the constituent correlations, and that forced this huge change in simulation numerics. Now, why did we need to fix that? Because the aircraft guys were laughing at us. The modelers couldn't do it. The aircraft people were mocking us incessantly. We had to do something. So we improved our numerics. And then that change fixed the problem, but it also improved some other aspects of our simulation. Now we can go to the next slide. The same principles were applied to solving the material derivative that you have in the basic equations of motion. And it developed a whole new dynamical core, the finite volume dynamical core. And this produced vast improvements in the general circulation models. The temperature biases disappeared. All kinds of things got better when we did this. So what we had been looking at and had been nagging problems for almost a decade turned out to be mostly an implementation issue, not a conceptual issue at all. Next slide. So this is just a summary of the pluses and minuses of the chemistry and transport models. Big minus, no predictive capability for long time scales, no feedback, and also you tend to start looking at events all the time and they hypnotize you. So you can't think anymore. So next slide. CTMs and CCMs have some components in common, same chemistry, same transport. The CTM has input met fields, the CCM, everything is calculated self-consistently. So the constituent fields, the radiation, and the dynamics are fully self-consistent. So clearly this is what you want to have. And we do have it now. In my branch, which is atmospheric chemistry and dynamics, we collaborate with the Global Modeling and Assimilation Office. And we've been trying to create this model from 1981 until we finally got it in about 2005. So that took us quite a while to get to this, to have a really good model. And this is dark, and I don't think you can really see it very well, but this is showing you one of the ways we use a CTM and a CCM together. This is MLS data. That's the microwave limb sounder, and what these showing you are contours of the horizontal gradients. And they're showing you that there's like very large gradients here in the southern hemisphere, high latitudes here in the northern hemisphere, and then very steep gradients in the southern hemisphere between the tropics and mid-latitudes. And what MLS is showing you is that these are sort of climatological features, and what this middle one is showing you is that in the CTM, using assimilated winds, that's real meteorology, we can do a pretty good job reproducing these features. But this one is showing you using the CTM, but now using the general circulation model meteorology, we can again reproduce these features. So that's sort of the question when you no longer have your model having the same meteorology as that in which you took the observations. You have to figure out novel ways of making your comparisons in order for them to make sense. But this is another example. This is a simulation. This is water going up in the tropics. So this is time, and this is pressure. And what happens, what I've plotted here is it's an anomaly plot. So you subtract it off the mean, and you can see that you have these seasonal areas of low and high water that propagate upward and maintain their integrity and don't mix. This is a really, really tough thing to do with a model and with numerics. Many, many things have to be right. You have to get the ascent. So this is the simulation, this is the data, and this is an overlay to show you that the slopes really are the same. So you have to be getting the ascent right, you have to be getting the correct relationship between water vapor and the tropopause temperature. You have to get the right seasonal variation in the tropopause temperature. You have to have this limited mixing between the tropics and the mid-latitudes. And this is an example of a basic state parameter that you really want to get right. Next slide. Can we test the coupling? So the answer to that is, yeah, we figured out some ways to test the coupling too. So what happens when the ozone hole forms is that the ozone, this is a 20-year trend. This is the average trend over 20 years. And the ozone hole is showing you as the chlorine increased between 1980 and 2000 that the ozone in this region went down. But it's also showing you this area higher up where the ozone went up. And what happens is because of this cooling, you have a change in the circulation, so it's going to try to go like this. And so the dynamics prompts this increase. And we got this as this was a model result, and we were looking at it, and I said to one of my friends, wow, a change that's that big, if that's real, we should see that in the data. And so we looked, and this is in the SPUV data, and there it is, the observed summertime increase in ozone that comes because of the cooling or lack of heating, you get a change in the circulation, and that causes the ozone to go up. And I don't have the plot here, but if I did this without the interaction, if I turn off the interaction between ozone and the circulation, then this maximum disappears. You still have the minimum for the ozone hole, but the maximum just goes away. This is another thing that shows you how to put all the data together from the Nimbus 7, URs, and Aura, and then hopefully some point out here in 2040 when my grandchildren have been instructed to check for me to make sure that the ozone is really going up. So what happens is if you look at the relationship between ozone and temperature, remember as chlorine goes up, it becomes less sensitive to temperature, and that's what you're seeing during this time period. As chlorine goes up, the coefficient that relates the ozone and temperature keeps decreasing. And chlorine leveled off, and our relationship has leveled off. And now our simulation says, as we continue on outward, about even 2030, we really ought to be able to tell that upper stratosphere ozone is recovered. And the cool thing about this is that it doesn't require you to have a continuous measurement. The top line is constant chlorine that shows you nothing happens if chlorine doesn't change. Next slide. I just want to say most ECMs now include tropospheric chemistry. It's much more complicated because you have to worry about weather scales and interactions with the land, interactions with the ocean, many more physical processes associated with convection. And so compared with trying to figure out how the model is performing in the stratosphere, figuring out how it's performing in the troposphere is a lot tougher. But obviously I wouldn't be telling you this if we hadn't come up with something. Can I have the next slide? So ENSO, going back to my Incan scientists and the Peruvians, the ENSO drives variability in ozone. So ENSO is El Niño Southern Oscillation. It's the dominant mode of tropical variability on interannual timescales. And one of my colleagues found that when you took the tropospheric ozone column in the eastern and western Pacific, this side and this side in these boxes, and you subtract one from the other, the average of 2 boxes, that it exactly tracks the ENSO index for many, many years. So we thought that was pretty interesting. And then we did a simulation. Can I have the next slide? And for our model, now, admittedly, we are not using an ocean model here for ENSO. We're using observed sea surface temperatures, but we're able to reproduce this exact same variability that is observed and the same sort of correlation with the ENSO index, which means that the way that the model responds to the changing sea surface temperature, moving convection, and changing its intensity and changing the circulation is appropriate. And if we look at the next slide, this is using data from the MLS and TESS instruments and the model. This is the data, and this is the model. And this is looking at the sensitivity to ENSO as observed by these Aura instruments and as reproduced by our model. And yeah, people bandy about the phrase good agreement all the time, but I hope that you'll think that this is pretty good agreement. And then these other contours that are drawn on here are showing you how the circulation is changing as a consequence of ENSO. So this isn't a chemical change mainly, it is mainly a caused by a change in transport. Can I have the next slide? But it's important. ENSO, remember, affects rainfall. Rainfall also affects agriculture and biomass burning, so it affects the emissions and the amount of pollution that's put into the troposphere. And in the tropics, lightning is a source of OH, and important to the oxidizing capacity of the troposphere and destruction of methane. So there's an ENSO relationship in OH and in that also. So if you want to really have an Earth system model, you need to be able to include processes like this one. Next slide. Coming attractions, right. For the stratosphere, chlorine is regulated, slowly decreasing. Many people think ozone depletion is a solved problem, but we're still kind of hoping that we're going to get to see it come back. But it's also true that the stratosphere responds to climate change. In the upper stratosphere, we have cooling, which means more ozone, but there's also circulation change in the stratosphere, which is having an impact. Can I have the next slide? All the chemistry climate models predict that the strength of the upwelling is going to increase over the next, 100 years. So we're here, moving out to here. Interestingly, of course, the models fall into two camps, where some of them are down here and some of them are up here. This one would have much bigger consequences than the lower one, because it affects not just ozone in the stratosphere and in the tropics, but also it affects the input to the troposphere and many other connections between these two regions. But so far, we haven't had enough change in circulation to be able to separate it and to be definitive and clear as to whether this is really happening. And the reason for that is that the actual atmosphere has some time scales of variability that we don't reproduce in these models yet. So there's still some development work that needs to be done. This is my summary. The need to predict whether it's weather, climate, ozone evolution is fundamental to atmospheric research. If we didn't have need to predict, you'd have a few people making curiosity-driven measurements, and that would probably be it. Modern chemistry climate models and the nascent Earth system models really do have their foundation in observations and analysis. And to evaluate global models, you need global observations to assure that you've got the base state right, to understand the response for natural variations, and then to identify, understand, and develop confidence in the parts of the CCM that control its response when you're trying to calculate something like climate change. Can I have the last slide? I didn't show you a lot of beautiful images because I really wanted to talk about some ideas more than I wanted to do a viewgraph movie. But there are really, really wonderful images. And if you look at some of these places, you can see them. You can even get movies from the Earth Observatory of all kinds of things, and they're just downloadable for the public. So thank you.
Thank you for that summary of these difficult problems. I'm Stu Anderson, the physics department, and so I'm monitoring the question and answer session here at the end. And so if anyone has any questions, just raise your hand and I'll bring you a microphone.
I really appreciated the imagery for the multi-step process related to the dryers and the washers that you had there. And I'm wondering how many times you had to explain this to your male colleagues.
The washer and dryer?
Yes.
They know by now.
Oh, okay, good.
I'm just curious what the state of funding is, and the whole government debate about, to keep the work going on, to keep improving the models.
Well, you've got two things. I mean, the bigger thing is that so you have the Earth observing satellites. Aura is the third. There's Terra, Aqua, and Aura. And Terra was launched in '99, Aqua in 2002, and Aura in 2004. We have nothing of that ilk on the books for the future. So it isn't just our stuff, it's the the observing system is the thing that's at the most risk at this point. For developing the models, from the NASA point of view, they're going to support developing the model as long as they're getting new data. When data is old, it's very hard to get NASA to be interested that much in funding it. We are doing our best to convince our program managers that you don't want to just be funding people to analyze the data that you got last week. And especially since you have this long record now from URs in 91 up till present, with overlap between the two of them, you really are starting to get a data record that's long enough to start to address some of these questions. For example, the one about the atmosphere varying on timescales that are longer than what we simulate. That's one of our current problems that we're trying to address. You know, funding, it's very competitive. It's difficult. And it's political. So.
So are you saying that there's no funding for any replacements for these satellites that you've been working with?
There's not a lot. I mean, there'll be a decadal survey coming again, but the projects aren't of the same scale as the projects that these were. So these were six-year satellites. That was our prime mission. Prime mission was 6 years. So if you've engineered anything, you know that if you engineer it for 2 years in space and it lasts for 10, that's a real bargain. But if you really want it to last 6 years in space, you've got to spend some extra money on it. So there aren't things that are being, and we have, there are examples. There's Calypso and CloudSat, which have made some really phenomenal measurements of clouds and cloud particles. One is a radar, one is a LiDAR, and really revolutionized our knowledge of cloud processes. Those were 2-year missions. They're both still operating. One of them's a little bit sick, but they are both still operating. You know, so you do have some really good success at getting long data records from short missions. The ozone, there is a plan to keep measuring ozone. I guess I don't think that you need to measure all the stratospheric gases all the time forever anymore, but there are a couple of things that you would want to keep an eye on. For example, stratospheric water. You would want to measure ozone. You would probably want to measure a trace gas, at least periodically, so that you understand if the circulation is changing or if something unexpected is happening.
Well, that's kind of my question. Just if you were going to design a new satellite, what would you tell the engineers to measure?
Oh, that's a really hard question. Well, that's sort of what I would do a simple one.
I'm an engineer, by the way.
Oh, yeah, I would do a simple one. The Canadians have an instrument called SciSat. Let me think. SciSat is the name of the satellite. ACE. It's the Atmospheric Chemistry experiment. It's an occultation experiment, so it measures profiles of many, many, many different constituents, but only, it makes sunrise and sunset measurements, so you get 14 profiles at each of 2 latitudes every day, and they move with the sun where they're going to be. SciSat is in an orbit that is inclined in such a way as to maximize the number of measurements over Canada, because it's a Canadian measurement. I wouldn't put it in that orbit, but if I could have an instrument like that, that would be great. That would let you keep an eye on everything. And it's relatively low cost, low maintenance, small satellite.
Other questions?
Along the same lines, how about the future simulation? Future satellite observations, but what about on simulation? The biggest changes?
Okay, so we're trying to make the Earth system model. So I think that the action over the next maybe 20 years is going to be at the interfaces, where the atmospheric model now is very well developed. The ocean model has some issues. The ocean-air interface and some gases, and what's going to happen if the ocean warms, and what will happen to those gases. There's some questions on that. The land, people really are interested in having an interactive land surface, particularly for things like methane emissions or for methane that may come from permafrost. So there's a lot of development work going on in land surface models, and then how you would couple them. The thing with coupling, and I don't think I made the point very clearly. When we first had general circulation models and we tried to put chemistry in, those models were so biased that all you were really doing when you put chemistry in the model was diagnosing the bias. You weren't learning anything else because the bias was too big. So when you couple a model, you really have to be concerned about bias and the actual physics of the interaction and the way that you represent it. And so the land surface model, the best resolution that we have, the land surface model wants to be subgrid. So there's going to be some real challenges there. I'm told at NASA, the main manager, Jack Kay is the guy, that he has no appetite for the does everything model. And I actually agree with that. Often you will hear someone developing a model and they'll be like, well, I've added this or I've added that, but without saying why this or that is important. Or I like to think of the model as a lot of resistors in parallel. You know, like you can only improve the model so much by improving one piece of it. You really have to approach all of the pieces. And so I would like to see people doing a measured approach to model improvement where you really demonstrate the need for a particular improvement before you go whole out and get everybody to do it. It's complicated, though. There's a lot of politics involved. I have to say, there's a lot of politics. All the countries of the world have their own model. They have different expertise. They push things in different directions. And then when it comes to assessment, and this is some of the stuff I'm going to talk in the talk tomorrow, when it comes to assessment, it's one model, one vote, and they won't vote anyone off the island. So it can be a pretty chaotic enterprise. NASA, if you want to do modeling and you get to do it at NASA, you are so lucky because we have not only the data, we have the mandate to use it. And lots of models, people are out there building models and they just don't bring the data to the picture. And whereas we bring it in all the time. You know, like anytime you get an impact of anything that you get in the model, you go, well, how can I observe that? Is that already in the data? How many more years do I need? What's the frequency? What's the resolution? What do I need in order to know whether this is real or not? And it's our whole mindset. And so I think it gives us a leg up. The other thing is hanging out with the experimenters. As a modeler, you never lose if you hang out with an experimenter because you learn a lot from them and you learn what's really important and you learn, well, it just sort of fixes some of the relationships in your mind in a way that you don't get them when you're really just looking at a computer screen all the time.
Other questions, please?
Lots of satellite projects cost $200 million, $600 million, $1 billion. During the last 10 years, there's been a lot of small satellites, microsatellites, student-developed in colleges or graduate schools. Has the microsatellite revolution of any value to you, or do you need such fancy instruments that they just have to be very expensive?
Well, I think that really depends on what you want to measure. I have talk with some people about some little microsatellite projects, and I think that they can play a role, but I also think that you're stuck with, if you're trying to do a model that works on 100-year timescales, you probably need measurements that will last a little bit longer. So I think that the microsatellites can be really useful if you want to investigate some processes, and that would be where I would be trying to direct my energy if I was trying to develop a microsatellite. It would be for process studies. And then some of these other things, they just need to last a little longer in space.
Other questions?
Like 10 years longer.
Anyone else? Well, perhaps we should thank Dr. Doug